Hello, and welcome to this video of application 301, Distributed Real-Time Computation System. I will first give a brief description of the application, then I will detail the architecture, explaining the decisions that we made, and I will show key parts of the source code to demonstrate how this was implemented. After that, I will show how to install the hardware and software and compile and run the software. Next, I will show the benchmarks from our testing with a full week of data and demonstrate the populated database. Finally, I will cover reporting and show some examples. This application is a system for importing and pre-processing huge amounts of log data in real time for subsequent reporting tasks. It includes specification of hardware and software used, as well as development of high-speed, high-volume software needed to perform this in real time. It does not include reporting, as that falls outside the scope of the current project. However, I will include some examples and explanations at the end of this video. The architecture of the solution. The first thing that we made a decision on was the operating system. We chose Linux servers for this application. It was clear from the beginning that we would be processing huge amounts of data as fast as possible, an area where Linux excels. We also wanted to use open source, freely available software wherever possible, to increase robustness, ease maintenance, and to maximize processing power for a given price. Additionally, in terms of processing power costs, Linux provides substantially more power using the same hardware. With regards to the database, we looked at dozens of different solutions, including various not only SQL, NoSQL options, and some systems, such as Apache Storm, which claimed to provide a complete distributed real-time computation system. The problem that we repeatedly came up against is that with available systems, we still need to provide custom software to do the actual log file processing, and often we were forced into using a much slower programming language, such as Java, which is certainly not suited to high-speed, high-volume applications. We found that by using C++ in combination with data bulk insert code, we could run many times faster than other solutions. MariaDB is the popular open-source branch of MySQL. It is very well tested and is used in a huge number of existing systems. If you have used MySQL in the past, you may well recognize it. It is almost identical, but it is fully open source and has some additional advantages. In terms of programming language, we chose to use modern C++ 17. That's the variant of C++ that was made standard in 2017. There is no language that can match the power and speed possible with C++ while keeping the maintainability of higher level programming. This is especially true of the recent additions to C++, such as move semantics, regular expressions, threading, and many other features which can be used to create programs unequaled in speed and power while maintaining clear legibility and maintenance. Our code is fully cross-platform, with no reliance on platform-specific code or libraries. So you can choose to use different platforms and compile the same code. Though if you do move to a different platform, you will sacrifice the very fastest processing that Linux supports. I am now going to have a look at installing the hardware and compiling and running the software. From our testing with the log files that you provided to us, we came up with a figure of 4 fairly recent PCs running Linux needed to be able to cope with the volume of data. That would mean that we could read the log files faster than they're produced and pre-process them into the database and make them available for reporting. Now, with more recent testing, since we added the bulk insert code, which speeds up our import into the database, we found that provided that we choose only a subset of the data to use, and I believe we can find a useful subset which will cover all reporting needs, we can even decrease that requirement to a single powerful PC running Linux with the database local. So that decision would be up to you depending on the amount of reporting you require. Now, the PC or PCs need to be installed on the same local area network as the host which hosts the log files. Our key bottleneck is in opening and reading the log files and then processing them on the server and then putting that data into the database. Now, if the database is on the same machine, that's the fastest speed of all for post-processing, but we still need to be able to read the log files as fast as possible. So it isn't sufficient to be able to have the files somewhere where they can be copied to the local area network. They have to be in some way mapped to it. For example, if they're generated on a different server, such as one of the web servers, if that server is physically connected to the same gigabit Ethernet, we could then share them using NFS, or if it's a Windows system using SMB, then we will be able to access the logs at sufficient speed that all of this processing becomes possible in real time. We cannot process the log files in real time if we cannot access them in real time. Once we've processed the log files, that will provide dashboard ability where we can report on what's currently happening with the system. But we would also want to do reports over accumulated data, over daily, weekly and monthly, perhaps even quarterly data. For that to happen, we need to keep some of the data in the database. So we can't simply pre-process it, put it in the database, run the reports, delete the data. We need to keep some subset of that data. And so when we are estimating the hardware requirements, we need to include the size of the database. Now, that database might be tens of terabytes if we have a very minimal set that we keep. So perhaps we want to do summary reporting for over the last 3 months data, but after that we don't go further back. We just keep summary reports. I should point out that when we do a search in order to create the data set that the report displays, we cache the result of that search, because that search typically produces a small set. It might typically be a table of numbers which is used to generate a pie chart or to generate some other kind of graph. So there's no overhead, or almost none, in storing those tiny tables. Therefore, we always cache every report. So once we've shown a report, we can show it again. It doesn't matter if it's a year ago, 2 years ago, it's stored in the database as a summary. What we can't do is regenerate it or include it in, for example, a longer running report. So our minimum, we think, would be tens of terabytes. These days, 14 terabyte hard drives are available and quite cheap. And if we put one of those in the Linux server and we used it for the database, we would then be able to store on that, and we wouldn't need an external disk array. If we decided we wanted to be able to generate fairly detailed reports over the past year's data, then we're talking about 100 terabytes or so, which would mean that the database server would need to have a disk array externally attached to it, perhaps through eSATA. We'll get to detailed numbers later on after we've looked at the benchmarks. I'm now going to take a brief look at the source code to show some of the key features, and then I'll show how we install and compile it. You will have received the DVD, which has absolutely everything on it. It has all the documentation, all the source code, as much of the sample data as we could, reports, all that sort of stuff. So you can access the source code from there. You can also access it from Bitbucket with the URL and password that have been previously provided. I will show you now the structure of the source code. So we're looking at the subdirectory which you get if you either check out the code from Bitbucket or you browse to it on the DVD. I suggest you copy it from the DVD to your local machine so that you're able to compile, because obviously a DVD is read-only. So there are two directories. One of them is the AIS 301 dist real-time comp, and that's where all of the source code is for this application. Under there, the server is under src, the source code. You can see we use ziplib in order to read the some of the data on the fly, which is provided to us in zip files. We save several steps in processing and make it even faster by reading directly from compressed files. So we do not decompress the file to disk, we decompress it to memory, and we read straight from memory in a streamed fashion. We don't need the amount of memory that would hold the entire file. So ziplib is used for zip. The key source code here is AIS 301, the CPP here itself. This is the one that includes our main program. Here it is. You can see main there. This is what happens when you first enter. So for example, if we run it like this, and you can see here the options that are shown. Let me show that now. I'm now on the build machine, and we can just run the code so that you can see that running. So I'm just doing -, which gives us the command line parameters. There we are. You can see them here. And looking back at the source code, you can see here how that's produced. This is standard C++ code. The way we've structured this is so that it's very, very flexible for making decisions about how much data to keep and how much to pre-process and then discard the original to keep the database size down, and also to keep the speed up. So every table that we use, we define in a C++ list. Here's general billing 3. So you can see it's very easy to define. This is defined directly from the documents that were provided to us, which tell us the data structure. Our code uses this to parse out the data, and then it uses it to create the table if it doesn't already exist in the database, and to populate the database. And there's a further step where it uses it for bulk file insert. Bulk file insert is a very fast way of getting a large amount of data into a database quickly. It works particularly well on Linux with C++ and obviously with SQL internally. I can show you that code. Under the database, we have database bulk insert. This is code written specifically for AIS for this project to make it really fast. And it stores the database connection and has a statement. And what it does is it builds up that statement with multiply parsed lines. So you get, in RAM, you get a larger and larger and larger list of pre-prepared data that can then be dumped straight into the database. It's a very fast operation. In fact, it even surprised us, and that's how we ended up with those numbers that you'll see in a few minutes. So, getting back to the flexibility, if you wanted to add a table, add a different log file, all you do is you define these in the same way as these are defined from the data that you provided us, and the server would automatically pick them up and put them into the database for you. Okay, here's the code where it actually runs. So it starts a database connection. It starts processing log files, and if it's been provided directories and asked to recurse, it will also go into directories. So you can traverse an entire tree, and in fact that's what we did for the week-long log files test. If you've asked it to monitor, then what it will do is it will keep track of all of the directories that were presented to it. Here we go, in a list. And if it is monitoring, it will then enter monitoring mode, which means that it regularly checks those directories for any new files. What this means is that the server will run permanently, and every time a new log file is encountered, it will look for only compressed ones. So it's when the web servers have finished with it, it will then read that and put it into the database automatically. Okay, let's get back to installing, compiling and running the software. So, here I am. I've copied this directory off the DVD or got it from Bitbucket, and I've cd'd into a subdirectory which is AIS 301 dist real-time build. I'm now going to clean the build. I simply do that by removing all files. Okay, so this is emptying the directory. Now I'm going to recreate the build files. This is all from checked-in code. And now I'm going to rebuild the server right here, simply by typing make. As you can see, it's first of all building the ziplib, and the external libraries are various compression. There are various compression algorithms supported. Now it's building our core code. You can see the percentage there on the left, 89% done. You would typically build this on the actual server that you're going to run it on, because then you would ensure that it has the same versions of the libraries that are installed on that Linux server. We're now compiling our database code, linking the executable. There's also some additional executables we've created for testing along the way. Now, as you can see, it's finished building and it's ready to run. The software that we require to be installed on the machine before you can compile is a C++ compiler, a recent one, so version 8.0 or later, and various client libraries, including the database, MariaDB client, Boost, which is a set of C++ libraries. It also needs to have network file access on the server, so that it can access the log files. And also on the primary one, you'd have the database installed. So in this example, we have MariaDB version 10.3 installed. We also have PHP installed for the reporting that we'll show you later, and Apache and PHP MyAdmin. All of this is also documented. You can read all of this in the documentation. So we've already created a database on this system. I will show you the database now. Here it is. I'm using PHP MyAdmin to access it. The database default name is nsri_raw, and you can see it's got a bunch of data in there already because this is from our testing. When you first create the database, there is no need to create any tables. The software will create any tables that are missing. So now let's show how we run the code. If we run it just with a question mark, it'll show all of the options. Key ones include if you want to change from the default database and database name, database user, database password, you can override it with the command line. I didn't do that with these tests. Then at the end of the line, you provide a path to where the log files are. You can provide multiple paths, and if you've set the recurse flag, you can also set multiple directories, and it will recurse right through them. So just point to the root, and then it will find everything. And if you're monitoring, it will then continue to monitor everything. Let me show you now the data that we used for the week-long test. So that is in a series of directories here. As you can see, 7 days, 1 week. There is an average of 24,000 log files in each directory, and there are also 7 zip files which contain multiple log files that you are probably familiar with. This is your standard data. The log files in here, I won't open it, it's so huge, are in gzipped format, so they have a gz extension, and our software reads these compressed files directly. It does not decompress them to disk. It only decompresses them as it reads them. It's even faster than decompressing and then reading. So we've run all of this data. It produced just a little under 2.4 billion lines of code. That's 2,367 million lines in those log files. So that's every single line in each one of these 24,000, these ones, every single line in the multiple log files within these zip files. It took the server 14 hours and 50 minutes. Now that was with the very latest code. It's a lot faster than we've seen in the past because we added bulk file insertion for the database, and we also added pre-processing so that we're storing data that the reports need, not necessarily data that we don't need in the reporting. So there was 168,600 compressed log files. The compression ratio was about 20 to 1. So each file is 20 times larger if you decompress it. The uncompressed size of the raw data was 2.4 terabytes, and the resultant database, because it does a lot of accumulation, so for example, every log file has lines with redundant data in it, user IDs or dates and times and so on are redundant. They're all combined in the database, and that also makes reporting faster. Once it's combined into the database, that created 42.5 gigabytes. Again, all of these numbers are available to you in the documentation and on the DVD. So let's have a look now at that database. I need to re-log in. So here are all the resultant tables. There are 26 tables here. And the size of the database, 42.5 gigabytes. So for example, one of the tables, which is used for making sure that two servers don't run the same log file, is the log files processed. And you'll see there's 168,603 lines because there's one row for every log file that was read. Let's have a look at those. We're looking at the first 25 now. Of course, the first 7 are simply those zip files, and then all the rest of these DA log files from various servers. Here we are recording the various sizes. Okay, we've almost come to the end of the video now. I'm just going to show you a little bit about reporting. Reporting is outside the scope of this application, out of this contract, but we've provided some example reports so that you can have for our own testing and to give a template for any work that you want to do. So you've seen the data. We'll now show you some reports run on that data. These are available online at the URL we've provided. So we've got a dashboard, video streaming analytics, and MPay analytics. Let's look at the dashboard first, which is designed to show you the current state of the system. So what we're keeping track of here, and you can keep track of a number of other features if you wish very easily. We're looking at latency, so we want to know if there's any problems with how fast the data is being returned. And here's the service time. So you see it peaks at 1 second, which is 45 million hits. If you drag over, you'll get more detail here. We're using standard charts that you can use yourselves. We'll show you in the code in a minute how that's done. And then here's some more detail using pie charts to show the relative popularities of the video resolution. So most of them are at resolution number 5. That was 168 million hits in that week. Status code, predominantly 200 as we would hope. 404 is second, which is file not found. And here's our catalogue, 88% live and 11% was video on demand. And we can also look at things like server balancing because this is the dashboard. So we're looking at which servers are doing the most work. And again, if you drag over it, you get the exact numbers. And here's how popular the different channels were. So the most popular channel there, number 3, at 60 million hits in this week. And we've got further drill down here for the dashboard for MPay. Now let's have a look at video streaming analytics. So let's say that we want to look for the whole week, an hour at a time, and we're only interested in hits. We could be looking at some other stuff. And here it is. So hits by hour over the last 7 days. Now this is the sort of detail where you need to decide whether you want to keep the data in the database and make it a larger database. If you want to do something like hits per hour over the last month or over the last year, I doubt you would, but obviously that would mean keeping an awful lot more data. And similarly, MPay analytics. Let's go over the 7 days and let's just look at login response. So, response by hour, we've got the blue line here represents success, and these are hits per hour. Login responses per hour. So it peaked at 10 AM, where there were 4,325 successful logins, and then there were another 188 which were code 1309. Let's look now at the source code behind these reports. So this is also available in your either checked in or on your DVD. Under PHP, we have a single PHP file which does all of the data retrieval to provide it to the web pages, and you can reuse this code. It's very general. What it does is it grabs the data requested and it also caches it, so next time you request it, it's instant. Some of these processes, the first time they run, can take a long time, and you may even want to do it overnight. So that's the PHP file, again with a default password and so on, and it can be used to grab any data that you want. So all the reports use this one PHP file. And then here's the HTML that you just saw. It's all one page despite being several tabs. And for example, here's a bar chart being generated. So here's the database query. It's a selection from the DA log data. And the dates are parameterized, so as you could see, we could choose whether it was over the week, over the month, and so on. The data is fetched here using this PHP code, and then bar chart is simply is in JavaScript. So what you're looking at here is JavaScript in HTML using Ajax to get the data, and then using open source charts, both jQuery and Google, to display the stuff. You see here using jQuery UI 1.1.2 and also using Google's static charts. Okay, so that brings us to the end of this first of the two videos. Any questions or comments, please just type them in below if you are on YouTube, or also you know how to contact us at Gifted Cloud and Scarlet Line. Thank you for watching, and I hope that it was a clear explanation.